So last week we talked about local maxes, local mins. We generalized the second derivative test to the second partials test. And then Friday we started looking at optimizing functions on closed bounded regions. Okay, so this is when we're trying to find the maximum and the minimum. And so, like all good things, we look back at what we did in Calc 1 and we tried to generalize that. So the Calc 1 or the Calc 3 equivalent of closed bounded interval, in other words, an interval that has a finite radius that includes the endpoints, would be closed bounded regions. So these are regions that can be contained within a finite radius and has the edge on it. If the function is continuous and we have a closed bounded region, then we're guaranteed there's a max and a min. That's the extreme value theorem. And then we find the critical points. So we look where the gradient is the zero vector, where the gradient doesn't exist. And then we go back and do some Calc 1 stuff on the boundary. So the examples we did, you sketch the region, you look at what's going on the boundary. You can find the max and min on the boundary that way. And what we're going to learn here, we're going to learn a method called Lagrange multipliers here later this week. That'll be an alternative way of finding the critical points on the boundary. But then what you do is you compare the biggest and smallest values you got on the boundary with the function values you get from the interior. The largest of those is the max and the smallest of those is the min. So it has the same idea behind it that the Calc 1 algorithm had. And so if you haven't done so already, I highly encourage you to go back and look at what we did in Calc 1, which is here. Compare that to what we do now in Calc 3. So last time we did example 5. We did through all that. And we talked about this a little bit at the end. This will come in more today, though. But back in Calc 1, you had this lone critical value property. If you had a continuous function on any interval, and you had only one critical value, if that critical value gave you a local max, then you could be guaranteed you had an absolute max. If the critical value gave you a local min, you could be guaranteed it was an absolute min. And the reason is, in one dimensions, you don't have a lot of room to move around. Let's say you've got a point here and it's a local max. If there were a function value larger than it, then if your function is continuous, at some point it has to turn around to get up there. You follow? And as soon as it turns around, you would be creating another critical number. So a lot of the optimization stuff you did in Calc 1, if you were on an unbounded interval or you weren't on a closed interval, sometimes you would appeal to this lone critical number property. This does not come over in Calc 3. And this was the example that we looked at. So we had done this earlier. I think we did this one either Wednesday or Thursday. But you only get one critical point, 1, 0. And if you go through the second partials test, you get a local maximum out of this. But if you look at f of 1, 0, and then compare that to f of negative 3, 0, f of negative 3, 0 is actually bigger than f of 1, 0. So it's not an absolute max. And then I encourage you to fire up Desmos to see that. So we want to kind of keep this in mind today, because some of these application problems in Calc 3 are going to have some extra thought behind it. So here are the guidelines for working applied optimization problems. Once again, there's no algorithm for these. It's like any word problem. You just kind of got to get in there and first things first, identify what you're trying to maximize or minimize. And here's a typo here. That should be an or. That should be maximize or minimize. That's called the objective function. And then assign variables as needed and use formulas given in the problem from geometry that relate the variables of the objective function. All right? Units can be a big help if you're not sure if your equations make sense. Also, too, sometimes they'll ask for things or they'll give you mixed units. They'll mix up like feet and inches, and you want to be consistent throughout. For what we're doing in Calc 3, we want to make sure the objective function is a function of just two variables. That just ties in with the nonsense we've been working on the past couple weeks. Determine a reasonable applied domain. Sometimes this will help you out. Sometimes this will take the region you're looking at from an unbounded region to a bounded region. For example, if you're trying to build a fence, length and width should be positive if you're actually going to have a fence. Then again, length and width can't, you can't be going off to infinity either. Okay. So this is where sometimes we have to do some extra constraints here, real world constraints. Check the reasonableness of your answer, and don't give up. We also have graphing tools now that'll help us understand what's going on. So here's an example. This may look familiar. We actually looked at this problem way back when we first started talking about functions of two variables. It's a profit function. The profit is measured in thousands of dollars by selling X hundred phones and Y hundred tablets. Find the maximum profit and how many phones and tablets should be sold to achieve the maximum profit. Now, since we're trying to sell these things, it makes sense that X and Y would both have to be bigger than or equal to 0. So in other words, we've already kind of reduced where we're looking here to quadrant 1. However, provided at some point there is positive profit, then the maximum would have to live in the zone where there's positive profit. Does that make sense? So it's helpful for us to figure out where the profit's going to be positive and just sort of look within that region. And so we can look at where P of XY is actually equal to 0. This would be our break-even condition. So we can go in there and we can try to see where we break even, and then we can try to then discern from that where we're going to be making money, where we're going to be making a profit, where we're not going to be making a profit. So as you look at this and you try to make sense of this, what kind of a conic section do you think this is going to work out to be? And how could we algebraically start manipulating the equation to help us realize what the conic section is? So this will help us narrow down the region that we're looking at. So what kind of conic section do we have here? Is it going to be a circle, hyperbola, parabola, ellipse? How do you know? Oh, how many variables are squared? 1 or 2? Yep, you got 2 variables that are squared, so it's not going to be a parabola. Are they the same or opposite signs? Same sign, so it's either a circle or an ellipse. Do they have the same or different coefficients? All right, so if it's going to be anything, it's going to be a circle. All right, so let's put this into sort of the standard form. We can get the add the x squared plus y squared to both sides to get them positive, and then subtract off the x, subtract off the y. And now to get this into standard form, I got to complete the square. So go ahead. The coefficients here of x squared and y squared are already 1, so I can go ahead and get stuff going here. Okay, so completing the square, I'm going to cut this in half. So get a negative 10 and square it, that would be 100. I'm going to cut this in half. Whoops, that's a negative 25 over there. Cut this in half, square it, get you a 25. And then add the 100 and add the 25. And so now, according to that, completing the square there, we should have two perfect square quantities. Sure enough, if I look at this is x minus 10 quantity squared. Plus, and this would be y minus 5 quantity squared. And the 25 cancels the minus 25. I'm left with 100. So sure enough, we got ourselves a circle. Where's the center of the circle? (10,5). Perfect. And what's the radius of the circle? Yep, radius 10. Good. Square root of 100, which is 10. So that's where we get the radius there. Okay, so we go back now to the region we're looking at. So we'll call that 10. We'll call this 5. So here's the center of that circle. It's got a radius of 10. So it's going to come over to here. So it's going to go up to 15. Going to go down to negative 5. And go over to here and go over to 20. So this would be the break even. All right, these would be all the combinations we would get where the profit is 0. Okay. Now the question is, where is the profit positive? Well, this curve breaks up the XY plane, breaks up the domain into two parts, the inside and the outside. So we can just kind of sample the parts here just to see where the profit's going to be positive or not. You can predict what's going to happen here. Just thinking about the geometry. You know, we've got negative x squared and negative y squared. So we should have an upside down paraboloid happening here. But we can test. We can test a point inside here. We could test actually the center, 10, 5. Let's see what kind of number we get. Welcome in. We get minus 100, minus 25, plus 200, plus 50, minus 25. So we can see what happens here. We get 100. Which is a positive number. So that means on our little graph in here, the inside here is positive. And I'll leave it to you. If you pick a number outside of this, like pick like 0, -5, even though it makes no sense to have a negative amount of things sold. If you pick a number down here, well, actually, we could just pick 0, 0. That's a quick one to get. If you look at P of 0, 0, you're going to get -25. So it's negative out here. So as far as positive profit's concerned, we only care what's happening inside this circle. And as far as looking at, realistic situations here, once again, the X and the Y should be positive. So we're just looking here in quadrant 1. So if I look at both of these conditions, so I'm not going to bother looking at anything below here. So this stuff doesn't matter because you'd be trying to sell a negative number of, what is that, tablets? Is the Y the tablets? Yeah. You can't sell a negative number of tablets, so nothing down there makes sense. And you'd only be looking at what's going on inside this circle because that's where we have a positive, right? So we know on the circle itself, the P of XY is 0. So now we're going to look for critical points inside here and then talk about what goes on this boundary here. So this is the boundary Y equals 0. So now we've taken this problem and we've narrowed it down to a closed bounded region. So the region R is this one. So it kind of comes up, does this. I already know what the profit here is. That's actually identically equal to 0. And we've got this boundary region here. That's the Y equals 0. So let's see what we can find. So our P of XY is minus X squared minus Y squared minus 20x, plus 20x plus 10y minus 25. Not 2y. Okay, so we're looking for critical points. So critical points are where the gradient is 0 or where the gradient doesn't exist. So once again, we look at this in terms of the partials. We're looking where the partials are either both simultaneously 0 or where the partials do not exist. So let's take the partial derivative here with respect to x. What do we get? So take a derivative with respect to x, treating y as the constant, negative 2x plus 20. And likewise, what's the partial derivative of p with respect to y? Negative 2y plus 10. Both of these partials exist everywhere, so it's just a matter of figuring out where they're 0 at the same time. So you got my system of equations here. And we saw this before because we got this quadric surface here. We get exactly what x and y are. What we get for x, what do we get for y? X is $10 and y is 5. Oh boy, that looks familiar. That's the center of that circle there, right? Which is, once again, we could solve this completely algebraically if we wanted to, but we're just demonstrating the method here. All right, so 10, 5 is the only critical point we get. Sure enough, that is inside the region here. And let's do the profit numbers here in red. So we'll put the profit here is 0. We know the profit here. We just did that one. That was what, 100, I think, inside. Now, let's look at this y equals 0 here piece. See what we want to do about that. Let's look at p of x comma 0 and see what that looks like. So once again, we're looking at this surface, we're intersecting it with the plane. Y equals 0. So all the y's drop out. I get minus x squared plus 20x minus 25. Excuse me, minus 25. Let's take the derivative of this to see where we get our critical point. Lo and behold, we get x equals 10 again. Oops. Which is directly below here, so that would be x equal 10 again. And so we could find p of 10, 0 to see what that looks like. And once again, we can kind of so y is 0, so it'd be just negative 100 plus 200 minus 25. So that would get us to 75. And then these 2 points, they're on the y-axis, but they're also on the curve where the profit is 0. So I know that those profits are zeros. And now I say, okay, well, what am I looking for here? I want to find the maximum profit. So I look for the biggest function value here. And the biggest function value here is what? So looking at the red numbers, what's the largest? Yep. The largest is 100, which means that corresponds to $100,000. That's at the point 10 comma 5. Once again, the 10 represents the number 100 phones and y is the number 100 tablets. So that would be 1,000 phones or 1,000 phones. And then 500 tablets. Okay. Any question on this example? It just gives a little context to the stuff we were doing Friday. But in order to use the stuff we talked about on Friday, you need a closed bounded region. So sometimes you have to work to get that. And so in this particular case, the assumptions we made is we're not going to sell a negative amount of phones. We're not going to sell a negative amount of tablets. That puts us in quadrant 1. But also, we assume at some point we're going to make profit. So we're going to look at the region we're actually making profit. And so that gets us to our setup here. Okay. Now once again, if you completed the square in general, because we did complete the square here, just to show you, you could do this one algebraically, but I wanted to demonstrate the calculus method here. You can complete the square on this in general, and then just one of the examples we did on Friday, we just looked at the geometry of things. So if you did want to complete the square in general here, you could factor out a negative leading coefficient here from the x squared and the y squared. Cut this in half and square it, there's your 100. Cut this in half and square it, there's your 25. You'd be adding in a negative 100. So to keep the balance, you'd be putting in your 100 there. You'd be adding in negative 25. So to keep the balance, you'd add your 25. And you could actually get your function itself to look like this. And you could argue all of this algebraically then. If you rewrite this, you could argue all of this algebraically. Because regardless of what x and y are, you're going to subtract 10 and then you're going to square it. You're going to subtract 5 and then you're going to square it. So this number here is either always positive or 0. And this number here is either positive or 0. We're subtracting these things from 100. So the maximum this could ever be is when both of these things are 0, because we're subtracting the least amount of stuff away from 100, namely we're subtracting nothing away from 100. So that's another way you could get this totally algebraically. All right. So this is a nice check for the calculus that we did. But once again, we're trying to just illustrate this procedure again. And then of course you could check this graphically on Desmos or GeoGebra. Okay. All right, let's take a look at example 8. This is a classic problem. These sorts of problems, box with no tops, is constructed from a material which costs $1 per square foot for the sides and $1.50 per square foot for the base. So the base, ostensibly the base costs a little bit more because we're trying to reinforce the base. For a cost of $25, find the dimensions of the box which will maximize the volume. So here we've got this here, a little schematic. We got the width x, the depth y, the height h. They're asking us to maximize the volume. So that's the first thing we do is we relate volume with the variables we've got. How do you find the volume of this box? Yep. H times x times y. So there's the volume of the box. They tell us the cost is to be $25. All right, so let's look at the cost here. So how much does it cost to make the box? Okay, it's constructed from material which costs $1 per square foot for the sides and $1.50 per square foot for the base. So let's look at the sides. So we have 4 sides altogether, but they come in pairs. We got the front and the back and the left and the right side. So how can we figure out the cost? That's the total cost. We got the cost coming from the front and back. Plus the cost from the left and right. All right. It says the front and back. It says the sides cost $1 per square foot. Okay, so I'm going to have to get the area of the sides and then multiply it by 1. So what's the area of the front? So I take area times cost per area. So what are the area of the front? If it's a rectangle, so it's going to be x times h. Very good. So I got an x times h, and there's going to be 2 of these, right? Because the front and the back are going to be identical. They're congruent. So that's going to give me the area. I multiplied by that the cost, which was $1 per square foot. Now left and right, what's the area of the left and the right here? So if I look at this side here, what's the area of that? Yep, that's y times h, and then we double that. 2yh times 1. So once again, that's area times cost per area. And now, that's just the sides. What am I missing here? What do we need? We need the base. So what's the area of the base? That's x times y times the cost, $1.50. Okay, so let's rewrite this so everyone's good here. So we've got the x times y, and we're assuming we're measuring x, y, and h in terms of feet. So x times y would give us feet squared times 1.5 dollars per square foot. That's your base. Plus your 2xh feet squared times your $1 per feet squared. This is your front and back. Plus your 2yh feet squared times your $1 per foot squared. This is your left and right. And this all adds up to your total cost, $25. So once again, the dimensional analysis here, you plug in the units. You've got dollars equals dollars. And so we got the equation 1.5xy plus 2xh plus 2yh equals 25. So this is sometimes called a constraint equation. We're not looking at all possible boxes here. We're looking at all possible boxes where we have the cost is $25. So another way to phrase this, and this we'll be talking about more when we get into Lagrange multipliers, the objective function, remember, that's the function we're trying to maximize or minimize. That's our volume that we're trying to maximize, subject to a constraint, and the constraint is 1.5xy plus 2xh plus 2yh equals 25. Now, for the stuff we've been working on, we need functions of just 2 variables. This is a function of 3 variables. So what we can do is we can use this constraint. We can use this constraint to help us solve for one of the variables in terms of the other 2. And so the question is, which variable do you want to solve for? We can solve for x in terms of y and h. We can solve for y in terms of x and h. We can solve for h in terms of x and y. And a lot of this then comes from, I mean, it kind of tells you which one to do. But why would it say solve for h in terms of x and y? What would be the advantage of that? Well, it goes back to the concept of symmetry that we were talking about before. If you look at the volume, if you interchange x and y, you get the same thing, right? Volume is x times y times h. That's the same as y times x times h. So the volume is symmetric in terms of x and y, but also the constraint equation. If you switch x and y in the constraint equation, you get the same constraint equation. Is that true if you switch x and h? Like if you took that equation and switched x and h, replaced, is it symmetric? So if you switched x and h, you would have 1.5hy plus 2xh, that would be the same, plus 2yx. Is that the same constraint that we had before? So if you look at the coefficients here, you can see it's different. All right? So these are not equivalent. So the reason we're solving x in terms of x and y is because that'll make the entire equation symmetrical. And then we can exploit symmetry. And essentially, if you have symmetry, that means you only have to do half the work. All right. So this is why we're going to choose to solve h as a function of x and y. So let's see how we would do that. I guess we would first subtract off. Whoops. So we have the 2xh plus 2yh equals 25 minus the 1.5xy. And then we could factor h out of here. And then divide it through. And there it is. So notice h is completely symmetric in terms of x and y as well. And so now if I look at my volume as a function of just x and y, I've got x times y times h. So that would be x times y times 25 minus 1.5xy over 2x plus 2y. That's now the volume, completely symmetric in terms of the variables x and y. And what that tells us then is that if we're going to have any critical points of this function, they're going to be the same. The x and y will be the same. That's why I'm saying if you do one, you get the other one for free. Any questions on the algebra there? Do you see why solving for h is a nicer choice than solving for x or y? You get that symmetry. So let's talk about the applied domain here. So here we got this function. And we're trying to maximize the volume. So technically speaking, if we're going to have a box, x and y have to both be what kind of number? So to even have a box, yeah, they both have to be positive. So we're going to be here, up here in quadrant 1. Are we going to have to worry about this being 0? If x and y are both positive, can that denominator ever be 0? No. So there we go. And that's about it. So the problem, so we'll get into it, but I mean, that's an unbounded region because it goes off forever. It's an unbounded region. Also, it's not closed. It doesn't have the axes on it. Now, if I really wanted to, I could sort of put most of the axis on here and most, I mean, you know, if I know what's going on here with volume. If either the x or the y is 0, then you got no box. Your volume is actually 0. Now, we could make an argument here at the origin when x and y are both 0, you would just have height but no base. That would also be a 0. So we could argue we could close that off, right? And the other argument is I mean, yeah, technically, you know, don't have any other restrictions on x and y, but we're building a box. Okay? So you can say, okay, well, we do have a restriction because we know what h is. in terms of x and y. H is this. It's 25 minus 1.5 xy over 2x plus 2y. That's going to have to be bigger than 0. And if our denominator is always going to be positive, that means that that numerator's got to be 0. So I need 1.5 xy to be less than 25. So I need y to be less than 25 over 1.5x. So I guess there's another restriction there. If we want the height to be positive, or once again, we could have it be 0. That's where the volume is 0. So we get this kind of a thing. So we would have that on our graph as well. And that looks like one of these things. So that does cut things down once again. On the red line itself, the volume is 0 because that's where the h is 0. But still, now we look at what we have here. It's between the axes and this hyperbola. You follow? This still is an unbounded region here. So then you could come in and say, okay, well, there has to be some sort of physical limit to the box you're going to make, right? Let's call that physical limit M. I don't know what it is. You follow? I mean, you can't be making these boxes that are light years, right? There's some physical limit as to what's going on here. So we'll talk about how to handle this in a minute. But we'd go in there and try to figure out our critical numbers. Or critical points. xy times 25 minus 1.5 xy over 2x plus 2y. And so we needed to figure out the vx and the vy. And once we got the Vx, we should be able to get the Vy using symmetry. And our critical points should have such symmetry. So did anyone get the Vx? I think I put it on here. So I think if you go through your quotient rule, this is what you should get for Vx. You do your low d high minus high d low, you square the bottom, off you go. And then you try to factor to see if anything comes out, but that would be your Vx. And notice when you get your Vy, you can check your Vy because we know the original function V is symmetric. And so notice going from Vx to Vy, all I do is switch x and y. So instead of having the y squared, it becomes an x squared. xy, yx, that's the same, but instead of an x squared, it becomes a y squared. So symmetry is pretty powerful here. You can check that. 2x plus 2y, you switch x and y, still 2x plus 2y. Okay? So let's talk about the algebra here. Okay? Because I know some of you need some algebra review. So let's talk about how we do that. So you got your y squared times 3 minus 4xy minus 2x squared over 2x plus 2y quantity squared. And then your Vy, once again, you can just swap out the x for the y. Go. So we're looking for the critical points. We're looking where the partials are either both 0 or where one of the partials doesn't exist. So as we mentioned before, since x and y are representing dimensions here, we're not going to have a box if x and y are both 0. So we don't really have to worry about the denominator being 0. So we're going to look at the numerators being 0. So here we go. We've got this going on. So if we're working under the assumption here that the critical point is going to be where x and y are both positive, so the denominators are positive. So the only way these fractions are going to be 0 is if the numerators are 0. So now we're down to this. Whoops. And once again, if we assume x and y are both positive, then we can divide out the y squared and the x squared, and we get this interesting system of equations. And so this is the kind of algebra I wanted to review here. For some of you folks, because this kind of thing comes up in some of the homework and whatnot. So I always get questions about this kind of thing. Because normally, you can do the old substitution elimination kind of a thing. And depending on, what you were taught, it's like, okay, you want to solve for y in terms of x or x in terms of y. Or when you do elimination, you're trying to completely eliminate one variable or the other. In this particular case, you can do sort of a partial elimination. Right? If you subtract these equations, you get 3 minus 3, which is 0. You can get the xy terms to drop out. And then you get 2x squared plus 2y squared is 0. So 2x squared equals 2y squared. So x squared is y squared. So x would be plus or minus y. Okay. And once again, since we're assuming x and y are both positive, we get down to the conclusion that x and y have to be the same. And so that's the symmetry that we kind of suspected we should get, right? If the function is symmetric in terms of x and y, all of the important points about the function should come from when x and y are the same, because the system, this whole system, can't tell the difference between x and y. There's nothing in the problem that distinguishes those two variables. Okay. Now, once you get x equals y, you can go back and then plug it into either one of these equations. So we can take this now and plug it back into here, and that'll give us what the x is. So you can go through here. You got a minus 4x squared, a minus 2x squared. That's a 6x squared. 3 x squared is a half. X is plus or minus square root of half. But once again, we're assuming x is positive here. So you can go through your square roots. Square root 1 over square root 2. Or root 2 over 2. And then you get the y that goes with it. But that's how you would get to that critical point. All right. So sometimes when you're solving systems of equations, don't get locked into the fact that you either have to solve for one variable or you have to completely eliminate one variable. Sometimes you can use algebra to simplify the relationships between the variables. All right. And this is especially important moving into the next section on Lagrange multipliers, because in the previous book we used to use, when we got to the systems of equations here, you get these nonlinear systems of nonlinear equations. It said that the solution methodologies require, quote, ingenuity, all right, which was just a fancy way of saying you're going to be spending a lot of your time trying to solve these equations. So I wanted to demonstrate this technique of getting rid of like this, just simply using algebra to simplify the relationship between the variables, all right. And it looks like I made a mistake here. What did I do with my Okay, so something's up here. Should that be a maybe that's a 25. I'll have to go back and double check. Looks like I'm off by my critical points. So I'll have to double check that. The algebra is the same though. But then you go through and get your volume at that point, 9.82 cubic feet. And then, how would you show that this actually gives you the maximum? Because you don't have the lone critical value property. You've got this critical value in here on this unbounded region. You know that the volume zeroes out on any of these things. All right? So you can think about how you would justify that what you found is actually a maximum. You could show it's a relative maximum, but that's just because that's a relative maximum that tells you that near that point it's the biggest volume. But then how would you conclude that it's going to be the biggest volume you can make? So I'll let you think about that. The method of Lagrange multipliers is a way to kind of get around this, but once again you have to justify that there's a maximum or minimum in the first place. All right, so I'm going to have to go back and double check this because I think there's a typo in this derivative. I think that 3 is supposed to be a 25, but the algebra is the same. Now, sometimes what happens in these application problems is instead of actually giving you a fixed number, like they say, okay, the cost is $25 per box, what if it's now C dollars per box? In other words, this is a fixed constant. Sometimes this is called a parameter of the system. So it's a constant that you can change. All right. So instead of going through and finding the solution for 25, what if I could vary that cost, right? So maybe I need to get to a certain volume, and $25 just isn't going to cut it. What would I have to increase that to? So oftentimes they'll have this this fixed parameter, and what you can do is go through the work in example 8, and everywhere you see a 25, just put in the C. So this would be your volume then. That'd be your volume. So notice instead of the 25 there, you get a C in there. And then I'll leave it to you. You should be able to get these to be your critical numbers. Okay. Notice they're in terms of C, and then the volume you get is in terms of C. So if there's a particular volume you need, like if you need the volume to be a certain amount, then this would tell you sort of the minimum cost you would need to get to that volume. All right. All right, so here's some homework to work on here. 74 to 76 even, those are some special problems. Usually the starter problems, once again, those are things that could turn into some nice projects. All right, so that's max and min problems.